Hello, welcome back, everyone. We are on lecture 10 of Fundamentals of Inorganic Glasses. This takes us to chapter 5 in the textbook. We're going to be spending the next 4 lectures on chapter 5. Chapter 5 is devoted to understanding some of the basic structures of different families of glasses, and we're going to be covering several of these families over the course of the next 4 lectures, starting with the most commercially important family of glasses, that is silicate glasses, as well as aluminosilicate glasses. So we're going to be covering what they are, what are they used for, and what are some of the basic elements of the structure of these glasses, and how does that structure contribute to their properties. So let's jump into it. We are going to start with pure silica. This is variously known as silica glass, vitreous silica, glassy silica. This is pure SiO2, and this is known as being the most refractory of all commercial glasses, meaning that it can withstand the highest temperatures. This is why it's used, for example, in the windows for space shuttles. Pure silica also has an extremely high resistance to chemical corrosion, very low electrical conductivity, very low thermal expansion coefficient, and also pretty decent ultraviolet transparency in the near UV. The main problem with vitreous silica is that it's very expensive to manufacture because of the very high temperatures that are needed. So the temperatures that are required are in excess of 2000 degrees C. This means that vitreous silica is really only used where it is necessary to use it because that level of purity is required. And what we're going to see is that there's various ways of making vitreous silica. One of them is melting high purity quartz, and the other way is a chemical route, which is based on reacting silicon tetrachloride with oxygen in order to deposit SiO2 soot. And these are classified as 4 different types of fused silica. So you'll hear people talk about, say, type 1 fused silica, type 2 fused silica, and so on. And when they refer to those different types, they are referring to the process by which fused silica is being made. The first 2 types of fused silica, type 1 and type 2, are made by melting of quartz. For type 1, the melting of quartz is done in an electric furnace, and for type 2, the melting of quartz is done using a gas flame. So both cases, they start with very inexpensive raw material, just quartz sand, which is one of the most abundant minerals available on the Earth's crust. And if you heat it up over like 1737 degrees C is the melting point, but up to around 2000 degrees C to get it to melt properly and get a good quality melt, and then cool it back down, then you would get fused silica. An electric furnace could be used if you wish to kind of minimize the water content of the quartz during melting. The gas flame could be wet, and so that could introduce some water during the melting process itself. Now, the downside of both type 1 and type 2 fused silica is that there are impurities in quartz. Any quartz that you dig up from the ground is going to have some level of impurities. It might be ppm, parts per million level. It might be ppb, parts per billion level of impurities. But there's always a very small trace amount of sodium. There's always some amount of water that is included in quartz. And this can actually be a serious problem when it comes to having the, say, either the high thermal resistance of the final glass product, or more often, the good optical transparency. Water is a particular problem because water absorbs at exactly the wavelength that is used for telecommunication. And really the biggest advance that needed to be made with inventing low loss optical fiber was getting the water out of fused silica. So in order to do that, we need to go to a chemical vapor deposition process. Type 3 and type 4 fused silica both involve chemical vapor deposition, reacting silicon tetrachloride with oxygen to form silica soot. With type 3 fused silica, this is done in a wet flame, so this doesn't really get rid of the problem of water. It could get rid of the problem of sodium impurities. But the good stuff, by far the highest quality fused silica, is type 4 fused silica. This is what is used to make all preforms for optical fibers, for all of the highest quality silica glass products. Those are type 4 fused silica. This is also known as high purity fused silica, or HPFS. So if you hear this acronym HPFS, this is implying type 4 fused silica, which is made via chemical vapor deposition in a water-free oxygen flame. So this is all done in a hood under a controlled atmosphere to make sure that the system is free of water. To give you an idea of how this works for making a fiber optic preform, so the outside vapor deposition process, which was invented at Corning Glassworks starting in the 1960s, this process involves starting with a target rod. Usually this is a silica rod that has already been made. And this silica rod is put in the atmosphere-controlled environment, and then two gases get fed into a flame that goes back and forth along the longitudinal direction of the rod. At the same time, the rod is rotating. So the rod is rotating, the flame is going back longitudinally, and wherever the flame goes, that's where silica soot is going to be deposited onto the target rod, and the silica soot is just going to grow outward more and more to form this preform. The key chemical reaction for this is taking silicon tetrachloride, SiCl4, and reacting that with oxygen gas. When those two react, they form silica, SiO2, and that also releases chlorine gas. There's two units here of chlorine gas. And this silica soot then gets deposited back and forth. Now, when making optical fiber, it is necessary to have a refractive index profile in the fiber. We're going to cover the details of why that is towards the end of the course in our lecture on fiber optics. But we need to have a higher refractive index in the inner part of the fiber, in the core of the fiber, in order to maintain total internal reflection of the light that's propagating through the fiber. The way to increase the refractive index is to dope the silica with germania. And in the same process, therefore, you can actually mix in some germanium tetrachloride in with the silicon tetrachloride. The more germanium that you dope in, the higher the refractive index. And then the ratio of silicon tetrachloride to germanium tetrachloride can be adjusted to change the refractive index as the preform is being built out radially. But the reaction there is analogous. It's germanium tetrachloride reacting with oxygen gas that is producing germania, GeO2, and then chlorine gas. Now, this preform itself is a soot. If you look at it, it looks like this. It's white because there's a lot of porosity in there that is going to scatter the light every time there's an interface. This preform is consolidated with a high temperature treatment. When it's consolidated, this is basically a sintering type of process. It's where under high temperature, there's viscous flow that's going to fill in the porosity and give this fully dense, very high quality silica. And in fact, if you look at this consolidated preform, you can see that there is like a little tube inside this outer tube. The one that you can see inside, that's visible because the core has a higher refractive index. This inner core is germania doped, whereas the outside cladding part is pure silica. And then as the third step, this is drawn into fiber by taking this preform, tipping it up vertically, and then the tip of the preform is heated up until it flows, and then that gets pulled down into a fiber. The fiber has a diameter of about 125 microns. That fiber gets pulled down, it is quenched rapidly, and then it is spooled at the bottom of the draw. And then those spools of fiber are put into cables, and this is what forms the backbone of the internet. And all of this was possible because of the invention at Corning Glassworks by Keck, Maurer, and Schultz of eliminating impurities from silica by going to this outside vapor deposition process, reacting silicon tetrachloride with oxygen to form silica, and doing so in a water-free environment. This was the key invention that enabled the development of long-haul optical communications. But what does silica look like from a structural point of view? Silica consists of tetrahedral units. The basic unit here is a silicon cation at the center of the tetrahedron. The silicon has a 4+ charge. This is bonded to 4 oxygens. Each of the oxygens have a -2 charge. And so if you sort of draw lines connecting the oxygens together, those form the edges of the tetrahedron, and the silicon cation is sitting at the middle of that tetrahedron. So each of these oxygens just has a single bond to the silicon, and then the other bond goes to the neighboring tetrahedra. So these oxygens are called bridging oxygens because they provide a bridging bond between 2 neighboring units. So you can see this here in part B of the figure, where there is a silicon tetrahedron here, silicon in the middle with the 4 oxygens. And this oxygen here, labeled O7, is a bridging oxygen that bonds to both of these tetrahedra. So this is providing a bridge between 2 neighboring tetrahedra. This next tetrahedron is bonded to its neighbor via a bridging oxygen as well. And if we were to expand out this entire network, you can see that all 4 of these oxygens are actually bridging. All 4 of them are shared. An example of that would be the central silicon shown here. The silicon is bonded to 4 oxygens, and each one of those oxygens provides a bridge to a neighboring silicon. And there is some randomness, of course, when it comes to how these tetrahedra are bonded to each other. And that randomness in the medium range order leads to a distribution of ring sizes. They could be as small as, say, a 3-membered ring, which is actually rather energetically unfavorable, but still possible. Larger 4-membered or 5-membered rings. 6-membered rings are very common as well. This is a 7-membered ring. In each case here, the number here, so 5-membered ring, refers to the number of silicons or the number of silica tetrahedra involved with making that ring. So you can just count the number of silicons around this ring, 1, 2, 3, 4, 5, and that's what gives us this 5-membered ring. So there's a distribution of ring sizes, and this is what gives us the disordered network of the silica glass. The table here on the left shows some average ionic pair distances in vitreous silica. So the bond distance between the silicon and its nearest oxygen to which it's bonded is 1.62 angstroms. The distance between 2 neighboring oxygens, so these are not bonded to each other, but just 2 of the nearest oxygens on opposite sides of a tetrahedron. That distance is 2.65 angstroms. Between neighboring silicons, it's 3.12 angstroms, and so on. There are different ways of showing this visually and depicting some of this ring structure. This is a drawing that shows some of these silica tetrahedra. And the key thing, if you remember Zachariason's rules, is that these polyhedra that make up the glass structure, in this case tetrahedra, they do not share edges with each other. They do not share faces with each other. They do share corners. And that corner sharing is enabled by sharing those bridging oxygens between neighboring tetrahedra. And as long as just one bridging oxygen is shared between a neighboring pair of tetrahedra, we know that that is a set of corner-sharing tetrahedra. So here we have this ring that shows 1, 2, 3, 4, 5, 6 tetrahedra. This is a 6-membered ring, and these tetrahedra are bridging each other via the bridging oxygens. Sometimes you will also see this expressed as a 2D projection. In this middle figure here, the dark circles represent silicons, and the light circles here represent oxygens. If you count the bonds, you'll see that there are only 3 bonds represented going from the silicon to the neighboring oxygens. There is an implicit understanding here that there is a 4th bond, and that 4th bond is just coming out of the plane. So sometimes you'll see this as a 2D projection where they don't necessarily show all 4 of the bonds because of this assumption of there being a 4th bond out of the plane. So just be aware of that and be careful when you're interpreting some of these structures. It's also quite common now to see computer-generated images of these glass structures, such as shown on the right. Sometimes these show the atoms explicitly, and sometimes they can be drawn with tetrahedra, as shown here. And this is something that can be done, for example, from molecular dynamics simulations. Now, one of the features of silica glasses are the bond angles. There are 2 bond angles to consider. The first is the angle going from the oxygen to the silicon to the oxygen. So this is an angle within the tetrahedron itself, the angle centered on the silicon itself. And this intra-tetrahedral angle has an optimum value of 109.5 degrees. This just comes from the geometry of a perfect tetrahedron, and the distribution around that tends to be fairly sharp. So this is a fairly rigid bond angle inside the tetrahedron. The other angle that we need to consider is the angle around the bridging oxygen. So this is the angle going from the silicon to the oxygen to the next silicon. This angle here that's labeled as beta about the oxygen. This tends to be a larger angle, and it has a fairly broad distribution centered at around 144 degrees. An example of this bond distribution of the silicon-oxygen-silicon angle is shown on the plot here on the lower right. This is peaking at around 144 degrees, but it has a really broad distribution. It could be as small as 120 degrees. It could be as large as a straight line, although that is fairly unlikely. But you can see this is a fairly broad distribution, meaning that there's a much greater amount of flexibility in the bond angle about the oxygen compared to the bond angle around the silicon. So a narrow distribution of the intra-tetrahedral angle and a broad distribution of the inter-tetrahedral angle. Now, some of the early models of silica glass go back to the 1960s. There's a famous model of the continuous random network of silica that was made by Bell and Dean. This is from 1966. This is an actual tabletop model of the structure of fused silica, where they took these principles of each silicon being bonded to 4 oxygens, each oxygen being bonded to 2 silicons, having rigid intra-tetrahedral angles and a greater flexibility for the inter-tetrahedral angle. And they use that to basically take Zachariason's rules and implement them in a real tabletop model. And they used this model to actually measure distances and calculate pair distribution functions between atoms just by taking a tape measure and measuring distances between atoms. That's how it had to be done back in the 60s because they didn't have molecular dynamics simulations back then. One of the early MD simulations of vitreous silica was done by Tom Soles. This goes back to 1990, and this included some of the early computer visualization of silica glass structures. Here's a more recent snapshot of an MD simulation of silica glass. And here The red atoms are representing the oxygens. They are bonded to the yellow atoms, which are the silicon atoms. And you can see how the silicon atoms here are 4-coordinated. The oxygen atoms are 2-coordinated. But one of the interesting things about the simulation is that it can capture some imperfections in the glass structure. There are defects that can exist. Some of the defects could include, as shown here, there is an oxygen that's bonded to only one silicon, so it's got a dangling bond on the other side. This is an unstable structure, and this is known as a non-bridging oxygen, or NBO. This is what the oxygen should look like, a bridging oxygen, where you've got a silicon bonded to the oxygen, bonded to the neighboring silicon. These defects, if defects occur, they will often occur in pairs because the pair of defects can charge compensate each other. For example, this would be a pair of defects that result from severing a bond between this silicon and this oxygen. When that bond is severed, you've got a non-bridging oxygen defect here on the right, and then a miscoordinated silicon on the left. So the silicon only has 3 neighbors. This oxygen only has 1 neighbor, and they could annihilate both of these defects by creating a bond between the silicon and the oxygen if they are drawn close enough together. And in fact, zooming in, you can see that this is an example of a 3-coordinated silicon defect. Another defect that could occur is an edge-sharing tetrahedron. According to Zachariason's rules, all the tetrahedra should just share corners, but every once in a while, a defect could occur, such as an edge-sharing pair. So if you've got 2 of the same oxygens from neighboring tetrahedra both connecting the same tetrahedra together, this is what gives you an edge-sharing configuration rather than a corner-sharing configuration. This is the same thing as having a 2-membered ring in the silica structure because there are 2 silicons here. This is a highly unstable structure, and so this, if it exists at all in real life, would exist in very small quantities. Now, the next family of silica glass that we want to cover is soda-lime silicate glass. Soda-lime silicate overcomes some of the problems of silica related to the expense of manufacture by lowering the temperature dramatically while also preserving some of the good properties of silica. As a result, soda-lime silicate glass is the most widely used glass. It's used for just about all beverage containers, windows and architecture and transportation. It's used for fluorescent lamp envelopes. And some of the key properties are its low cost. It's made from very cheap batch materials, quartz sand, soda ash, limestone. Its chemical durability is not as good as fused silica, but it's good enough for most applications. It's good enough for most beverages, for food packaging. And the transparency is not nearly as good as fused silica, but it's good enough for everyday items like windows, where you only need transparency through the thickness of the glass. So you just need transparency through a few millimeters. We're not using soda-lime silicate for long-haul optical communication. That would not work at all, but it can provide good transparency through the thickness of a window or through the thickness of the wall of a glass container. One of the downsides of soda-lime silicate is that it has a much higher thermal expansion coefficient compared to fused silica. It's about 95 times 10 to the minus 7 per degree C. And as a result, it's much more prone to failure from thermal shock compared to fused silica. So if you take soda-lime silicate from high temperatures and you quench it rapidly, maybe by submerging it in ice water, it'll probably break. And so you need to be really careful about that. Large-scale continuous melting of inexpensive batch materials like soda ash, which is sodium carbonate, limestone, which is calcium carbonate, and quartz sand, which is silica. And this melting is possible at temperatures of around 1450 degrees Celsius. And so this is what makes it possible to make products inexpensively and with high throughput. So this is why soda-lime silicate is by far the most commonly used glass in the world and has been for quite a long time. Now, the way that the melting temperature of the glass is lowered, and this is also the reason why the thermal expansion coefficient goes up, is that these additional components in the glass, the sodium and the calcium, act to create non-bridging oxygens. So what they do, let's consider an alkali oxide M2O, such as sodium oxide. And by the way, if you take soda ash and you melt it, it's going to convert to sodium oxide. That sodium oxide gets incorporated into the glass, and then carbon dioxide is released in the process. Same thing with limestone. The limestone calcium carbonate decomposes to calcium oxide, releasing carbon dioxide in the process. So in the glass structure, what we care about is the oxide form. So sodium oxide, Na2O, or calcium oxide, CaO. And what this does in the glass structure is that we start off with this bridging oxygen between two neighboring silica tetrahedra. So you've got two neighboring silica tetrahedra, a bridging oxygen between the two. And then that reacts with one formula unit of the alkali oxide, like sodium oxide. And this sodium oxide attacks the bridging oxygen bond. It breaks the bond. And then the dangling bond on one of the oxygens here has a net charge of -1 because the oxygen has a charge of -2. One of those negative charges is compensated by bonding to the silicon. The other negative charge is then compensated by forming an ionic bond to the alkali modifier ion, this M plus. And then, so one of the modifiers from the M2O unit here goes to charge compensate one of the non-bridging oxygens. The other alkali modifier ion and the other oxygen are then bond to the silicon from the other neighboring tetrahedron. So rather than having a three-coordinated silicon here with no oxygen, it takes the oxygen from that alkali oxide unit, bonds to that, and then this oxygen has a net charge of -1. That gets compensated by the other remaining modifier ion. So as a result, everything is charge compensated here. The dangling oxygen bonds are compensated by the positively charged alkali modifier ions. But the net result is that we've broken a bond here. And so what this means is that we've converted this non-bridging oxygen to two non-bridging oxygens. And we have broken the connectivity of the glass network such that these two neighboring silica tetrahedra are no longer bonded to each other. If they're no longer bonded to each other, that means they can flow more freely with respect to each other. That means that the glass has a lower viscosity. That means it can melt at a lower temperature, but that also means that it can expand more upon heating, which is what gives it its higher thermal expansion coefficient. So breaking up these bonds is good for lowering the melting temperature. It's good for making the system more fluid, but we pay the price in terms of having a higher thermal expansion coefficient. You can see this kind of visually as well if you consider this picture here where there's a bridging oxygen between two neighboring silica tetrahedra. And then when the Na2O is introduced, it breaks up that bridging oxygen. The oxygen from the Na2O formula unit goes to one of the silicons, and then the negative charges that remain on the oxygen are balanced by having ionic bonds to the positively charged sodium. What about divalent cations? So each divalent cation, like calcium or magnesium or strontium, with a 2+ charge, they can create two non-bridging oxygens. So if you've got calcium oxide that comes in, the calcium oxide will break up this bridging oxygen bond, and it will form two non-bridging oxygens. The calcium oxide formula unit is bringing in one of the oxygens. Each of the oxygens has a dangling bond with a -1 charge. The calcium has a +2 charge, so it's able to charge compensate both of them. So it forms a weak ionic bond that provides kind of a bridge between these two tetrahedra, but that bond isn't nearly as strong as the bond provided by the bridging oxygen. And so this breaks up the network. It doesn't break it up as effectively as sodium because there's still kind of this weak ionic bridge across them. but it does end up lowering the melting point. So a combination of sodium and calcium strikes the right balance between breaking up the network while also continuing to have good chemical corrosion resistance of the soda-lime silicate glass. So this creation of non-bridging oxygens is made by introducing these network modifiers, sodium oxide and calcium oxide, into the glass network. This decreases the connectivity of the glass network, which means that the local parts of the structure can flow more easily. That lowers the viscosity of the system to enable easier glass melting, but we do pay that price with a higher thermal expansion coefficient. Here you can see kind of these projected 2D images of soda-lime silicate glass structure, where you've got a silicate network. So the network former is silica, and the basic structural unit is still the silicon tetrahedron. What the network modifiers do, either sodium or calcium, what the network modifiers do is they change how those silica tetrahedra are bonded to each other. So instead of having all four of the corners of the silica tetrahedra being shared, now for a large fraction of these, only 3 out of the 4 corners are shared, enabling greater flow. And the more modifiers that you add to the glass network, the more that breaks up the connectivity of the network because you're forming more and more non-bridging oxygens. And that brings us to the way to quantify this, and that is through what's called QN speciation. QN, where this N indicates the number of bridging oxygens for a given tetrahedron. Sometimes you'll see this expressed as a subscript. Sometimes you'll see it expressed as a superscript. There's not really a standard way of describing this in the community. But this, regardless of where you put it, the little n represents the number of bridging oxygens. So if we start off in pure silica, SiO2, we start off with all Q4 units. So if you consider the central silica tetrahedra, all 4 of these oxygens are bridging to neighboring tetrahedra. That's why this is called a Q4 unit, because there are 4 bridging oxygens. When the first modifier is added, this breaks up one of the bridging oxygens, and the Q4 unit then converts to a Q3 unit, where now the central tetrahedron is only bonded to 3 neighboring tetrahedra. If you continue to add modifiers, that would create a second non-bridging oxygen on that central tetrahedron, and that converts the Q3 unit to a Q2 unit. And now look at this. This no longer satisfies Zachariason's rules, right? Because Zachariason said at least 3 corners must be shared. He said that at least 3 corners must be shared because we need to build up a random network in 3 dimensions. And if you only have two corners shared in this Q2 unit, then this is just going to form a long chain. And so this would be unable to build a stable 3-dimensional network. So if you want a stable glass network that satisfies Zachariason's rules, that needs to be composed of some combination of Q3 units and Q4 units. Fused silica is entirely Q4 units. Soda-lime silicate is a combination of Q3 and Q4 units. If you add too many modifiers, the glass will start to become unstable. Then you'll get these Q2 units. Eventually, you'll get Q1 units. This is even less stable because this is just kind of an isolated dimer, or just, these tetrahedra are just bonded to each other, just one other tetrahedron with, no connection, no strong connection to the rest of the network. In the extreme case, you could also have Q0 units, which is just a silicon tetrahedron molecule floating the structure, and that would be extremely unstable. Now, if we plot the distribution of these QN species as a function of modifier content, we would, of course, start with 0 modifier content with 100% here as Q4. But as the modifiers are added, this starts at around 16% or so modifiers. And for this particular plot, you can see how the Q4 concentration is decreasing. So the Q4 concentration is decreasing, and eventually this comes down close to 0. The Q4 is decreasing because the fraction of Q3 is increasing with modifier content. So the Q3 actually starts at 0, and then it increases from there as modifiers are added, goes through a peak, and then it turns around and goes back down as the Q2 units start to form at higher modifier concentrations. Q2 will go through a peak, and then Q1 species take off. And the region where we have good glass formation is where we've got some combination of Q4 and Q3 species with a minimal amount of Q2. So basically, this region here of around 20 to 25% modifier content is where we usually like to be. And that's because we can lower the melting temperature of the glass while still having good connectivity to form a stable glass structure in 3 dimensions. Now, this was kind of discussed under the assumption that all of these modifiers are going to be kind of randomly distributed in the glass structure. There is a modification to Zachariason's continuous random network model called the modified random network model, which was proposed by Neffel-Greaves, where Greaves noted that there is actually some degree of clustering of the modifiers, meaning these dark atoms here are modifier ions, that they don't just randomly distribute in the glass structure, but they tend to cluster and form kind of channels in the glass structure. And these channels would correspond to the regions of weakest bonding within the glass. So if this glass breaks, it's more likely to break along one of these channels, according to this modified random network model. So the modified random network model is basically saying that there's some clustering of modifier species leading to these types of channels where the bonding is weaker within those channels. Now, if you add too many modifiers, if the modifier concentration becomes too high, you end up with a lot of, these are Q1 units here, Q2 and Q1 units, maybe even some Q0 units. And what happens here is that there's no rigid network, right? There's no rigid 3-dimensional network being built because there aren't enough bonds. And these are what's called invert glasses. Invert glasses are where the modifier concentration is higher than the network former concentration. And for invert glasses, these glasses no longer form a continuous network. So these glasses are highly unstable. They're basically just studied right now as a scientific curiosity, and they aren't really useful for any technological applications because they just degrade so quickly. They will corrode from the humidity of the environment, or they will crystallize easily. So moving on, so we covered vitreous silica, we covered soda lime silicate. The final family of glass in this lecture is the aluminosilicate glass family. Aluminosilicate glasses are very important for a wide variety of applications. Sodium aluminosilicate glasses are the Gorilla Glass that is the cover for your smartphone. There's alkaline earth aluminosilicate glasses that make up this willow glass, which is a very thin, flexible glass. Other types of aluminosilicates are used for fiberglass that can be used as fiberglass insulation or fiberglass composites for making vehicles such as this Corvette, or boats as well tend to be made from fiberglass composites. So aluminosilicates are everywhere. If you just add alumina to a glass network, it's actually rather unstable on its own. There's some controversy around what the exact structure is of alumina, but the alumina comes in as a 3+, which means that there would be 3 stronger bonds to oxygens. On the left here, this is depicting kind of ionic bonding of 3 oxygens to the aluminum. In that sense, the aluminum in this case is acting a little bit more like a modifier compared to a network former. And then there's 2 or 3 other bridging oxygens from neighboring silica tetrahedral units that just happen to be in the neighborhood but aren't providing strong bonds. Alumina is really unstable in this type of a configuration. Alumina desperately wants to be in a tetrahedral configuration. And one of the ways to do that is to form a defect on the oxygen. Aluminum just has a 3+ charge, and so if we create a compensating charge defect on the oxygen, by making an oxygen 3 coordinated instead of 2 coordinated, that could charge compensate the aluminum, so the aluminum could stabilize in a tetrahedral configuration. So this is called an oxygen tricluster. The alumina tetrahedra could form a tricluster with 2 silicon units, as shown here, or it could form a tricluster with a silicon unit and another alumina unit, which is probably less favorable. There's something in aluminosilicate literature called the aluminum avoidance principle, which states that the aluminum bond is unfavorable. And so this is less likely to occur, but it's still a possibility. Another possibility would be having kind of a tetrahedron where there's 3 ionic bonds between an Al3+ cation and 3 non-bridging oxygens here, and then a 4th bridging oxygen. This is also kind of not very stable because of the weaker bonding that would form in this case. So none of this that I'm showing you is a very stable configuration for aluminum. Probably the most likely here is using some oxygen triclusters with some combination of neighboring bridging oxygens. But what is much more favorable for aluminosilicate glasses is to charge stabilize alumina in a tetrahedral configuration by bringing in a modifier like sodium. So aluminum has a 3+ charge. In order for it to form a stable tetrahedron, it needs to have an effective 4+ charge. And one way to do that is to bring in a modifier cation, such as sodium, and sodium has a 1+ charge, and together the sodium and the aluminum can act as an effective 4+ charge. So 3+ from the aluminum, 1+ from the sodium would give an effective 4+ charge, and that would then stabilize the aluminum in this tetrahedral configuration. And what's interesting about this is that this gives a different structural role for the same modifier ions that we just discussed in soda-lime silicate. So remember, in soda-lime silicate, the sodium creates non-bridging oxygen, so it actually destabilizes the glass network by breaking apart bonds. In this case, with the aluminosilicate glass, the sodium is actually stabilizing the glass network because it is helping the aluminum to be in its preferred structure, which is this tetrahedral structure. And so the sodium in this case is not forming a non-bridging oxygen, so it's no longer breaking up the glass network. It's actually strengthening the glass network by allowing aluminum to form these strong bonds with 4 other oxygens. And this is, one of the really interesting things that we're going to come back to in the next lecture when we deal with borosilicate and boroaluminosilicate glasses, is that the same modifiers can play different structural roles depending upon which network formers are there. And I'm going to return to this next time when we cover boroaluminosilicate glasses, where we will see that the same network modifier, sodium, can have 3 very different structural roles depending upon whether the sodium associates itself with a silica, a boron cation, or with an aluminate unit. But for this lecture, I want to end this one with our class great. Today, it is Bertram Warren, who lived from 1902 to 1991, born in Waltham, Massachusetts, outside of Boston, and he was one of the world's foremost experts in X-ray crystallography. He had a long career at MIT, where he experimentally confirmed Zachariason's random network model of glass structure. He followed up on this groundbreaking research with extensive studies of glass structures for a variety of different chemistries, and provided a lot of key insights into the structure of both silicate and borate glass families. And we are still benefiting from his work today. During his lifetime, Warren was well known for his kindness, humility, patience, as well as his creativity and scientific rigor. So to summarize, pure silica, fused silica, or vitreous silica consists of a random network of corner-sharing silica tetrahedra. In pure silica, all four of the oxygens are bridging oxygens. We can form that either by melting of quartz, which is type 1 or type 2 silica, or by chemical vapor deposition, which is type 3 or type 4 fused silica. Doing chemical vapor deposition in a water-free environment gives you type 4 fused silica, which is high purity fused silica. And that is how optical fibers are made. But for most common everyday glasses, we want to lower the melting temperature. That's done by adding modifier ions like sodium and calcium. They convert bridging oxygens to non-bridging oxygens. That lowers the conductivity of the glass network, which lowers the melting point, but also increases the thermal expansion coefficient so that they're worse for thermal shock. We can describe this conductivity of a silicate glass using this QN speciation designation. And if we've got an aluminosilicate glass, the modifiers play a different structural role because they are needed to stabilize the 3+ aluminum into a tetrahedral configuration. So the modifier, like sodium, has a 1+. The 1+ from the sodium combines with the 3+ from aluminum and forms an effective 4+ charge. So next time we continue on with chapter 5, and we will deal with borate glasses and borosilicate glasses, and also at the end, boroaluminosilicate glasses. Thank you again for watching, and please reach out anytime if you have questions.